Okay, I want to apologize. I lost the copy of the paper that I was working on, so to some extent I'm starting over here with my comments. Again, commenting that this this section here was nice in terms of how you defined each of these forces. Now, in terms of the equation derivation, as I mentioned in the first part, all this stuff up here needs to be included in the text, sort of in a step-by-step fashion. All these words down here like this. The forces associated with the y-axis are weight of the block, normal force, y component, the x component. Next we solve for the normal force. So like right in here you can have things, you know, your x-axis equation, and in here your y-axis equation, and then you can go ahead and rearrange your y-axis equation, and then you can show this step. So in between each one of these sentences needs to be these equations. That's the proper way to do a derivation in a scientific paper. All right, on to the results. So your results show just as you were saying, that the greater the angle, the more the tension force. Okay, so again, I had a little technical glitch there. Let's go to your results here, where you're pretty clear about the gradual increase that you mentioned in your abstract, and the sort of the takeoff where it really begins to pick up there. Now, one thing that I'll mention is that this line, again, is this a math fit, or is this the model? You can have a mathematical model, but it's best if you have the mathematical model not just be simply a best fit, but rather, you know, based on some physics. And that was the whole purpose of this experiment. Now, as I recall from some discussions with Nick, your model was more down like that, with your data points sitting, you know, sitting up here where you've got them. Then, in addition, your model has some uncertainty associated with it. So, based on the uncertainty in your mass, and probably more important, the uncertainty in your coefficients of friction, there should be sort of a range in predicted tensions. And you could do that as error bars around your model. Or another neat way to do it is to do it as sort of upper and lower bounds to the model. And then in the ideal case, these data points fall in here, but they don't need to. Now, there's something else that I wanted to point out, especially if this is, which is what I think it is, a mathematical fit. What you miss by that is the fact that this starts to come back up again. And so you actually have a minimum. In fact, all of your statements here about it, you know, increasing up and up, actually miss a very important feature, which is a local minimum right there. And that local minimum can be found by either A, looking at the graph, or B, with some taking of derivatives of this function. I want to go back up to your model for just a second. I noticed that this here is, I noticed there's a negative sign there, and I think if you do the math, that negative and that negative make that a positive. And that's another thing that leads me to believe that on this page we don't have, you're not showing the fit of you're not showing a model there. So that's what you need to do. You need to have that mathematical statement translate onto this graph and then overlay the data there.